Video lecture on digital modulation schemes by J. Janita Jabaneza, working as Associate Professor in the Department of Electronics and Communication Engineering, Panimala Engineering College, Chennai. Contents covered in this video lecture are generation and detection of BPSK, BFSK, DPSK, QPSK and QAM. Passband transmission model. So the diagram shows the passband transmission model. Here the message source emits one symbol per TB seconds with equal probability. That is, it will be emitting binary zeros and ones with equal probability. That is applied to the encoder, wherein the encoder will be converting the binary zeros and ones into a line coded waveform by assigning plus 1 volt for binary 1 and minus 1 volt for binary 0. This is applied to the modulator. The other input to the modulator is the carrier signal S of t, which is equal to square root of 2EB divided by TB cos 2 pi FCT, where EB is the bit energy and TB is the bit duration. The output of the modulator is the modulated signal or digital modulated signal, and that is transmitted through the communication channel. Since we are transmitting the message in the modulated form, it is called as passband transmission. At the receiver, it is received by the demodulator, wherein it will be converting the modulated signal into a line coded output, and that in turn is applied to the signal detector in order to generate the binary 0 and 1 what we transmitted. So digital modulation uses frequency, phase and amplitude variations of the carrier signal with respect to the binary ones and zeros. Since the characteristics of the carrier will be shifting based on the values of ones and zeros, the digital modulation schemes are also called as shift keying techniques. So based on frequency, phase and amplitude, we have frequency shift keying, phase shift keying and amplitude shift keying. Binary phase shift keying or BPSK. BPSK is a digital modulation technique in which the phase of the carrier is modulated or shifted in accordance with the digital input 1 and 0. Next we will see the mathematical representation of a BPSK signal. Let us consider the carrier signal as S of t, which is equal to square root of 2EB divided by TB cos 2 pi FCT. Whenever we are transmitting a binary 1, the same carrier is transmitted. So we can represent the signal for binary 1 as S1 of t, which is equal to square root of 2EB divided by TB cos 2 pi FCT. But for a binary 0, the carrier will be having a phase shift of 180 degrees. Hence we can represent the signal for binary 0 as S2 of t, which is equal to square root of 2EB divided by TB cos 2 pi FCT plus pi, which in turn will be equal to minus square root of 2EB divided by TB cos 2 pi FCT. So in general, we can write the equation for BPSK signal as S of t, which is equal to B of t square root of 2EB divided by TB cos 2 pi FCT, where B of t will be equal to plus 1 when binary 1 is transmitted and it will be equal to minus 1 when binary 0 is transmitted. With this introduction, we will see how to generate a BPSK signal. So the diagram shows the transmitter of a BPSK signal. So here the binary data is applied to binary NRZ level encoder to generate the output B of t. This B of t is applied to the product modulator. The other input to the product modulator is the carrier signal S of t equal to square root of 2EB divided by TB cos 2 pi FCT. The output of the product modulator is the BPSK signal. Say for example, once we are transmitting a binary 1, binary NRZ level encoder will be assigning plus 1 volt for binary 1. So now the product modulator will be multiplying plus 1 volt with the carrier signal in order to generate the signal S of t equal to square root of 2EB divided by TB cos 2 pi FCT. When we are transmitting binary 0, the binary NRZ level encoder will be assigning minus 1 and the product modulator will be multiplying minus 1 with the carrier in order to generate the signal S of t, which is equal to minus square root of 2EB divided by TB cos 2 pi FCT. So this is how the BPSK signal will be generated. So the generated BPSK signal will be transmitted and at the receiver it will be received by the receiver. So the receiver will be having a multiplier followed by the integrator and decision device. So the multiplier and the integrator together will be called as a correlator. So the received BPSK signal is applied to the multiplier. So we know the received BPSK signal will be plus or minus square root of EB square root of 2 by TB cos 2 pi FCT. The other input to the multiplier will be the carrier signal, which is equal to square root of 2EB divided by TB cos 2 pi FCT. Since we are using the same carrier what we used in the transmitter in order to demodulate the signal, this type of detection or demodulation is also known as coherent demodulation. The output of the multiplier is indicated as C of t, which will be equal to plus or minus 2EB divided by TB cos square 2 pi FCT. This is applied to the integrator. So the output of the integrator is indicated as S1 of t, which will be equal to plus or minus 2EB divided by TB integral 0 to TB cos square 2 pi FCT into dt. On simplifying this, we get S1 of t as equal to plus or minus EB, and this is applied to the decision device. Already the decision device will be provided with a threshold value equal to 0. So now the output of the decision device will be such that it will be equal to 1 when S1 of t is greater than 0. Otherwise it will be equal to 0. That is how the binary data will be obtained at the receiver of BPSK. BPSK waveform. So we know very well, whenever we are transmitting a binary 1, the same carrier will be transmitted. But while transmitting a binary 0, the carrier will be having a phase shift of 180 degrees. So this is what is indicated in the BPSK waveform. Now we'll see how to plot the constellation diagram for BPSK signal. So we know very well, for a binary 1, the signal which is transmitted is S1 of t, which is equal to square root of 2EB divided by square root of TB cos 2 pi FCT. Whereas for binary 0, the signal is S2 of t, which is equal to minus square root of 2EB divided by square root of TB cos 2 pi FCT. Let us assume psi 1 of t as equal to square root of 2 by TB cos 2 pi FCT. So now substituting square root of 2 by TB cos 2 pi FCT as psi 1 for the equation of S1 of t and S2 of t, we can obtain S1 of t as equal to square root of EB into psi 1 of t and S2 of t equal to minus square root of EB into psi 1 of t. So now the psi 1 of t is called as the basis function. I am going to consider an imaginary line on the x-axis indicating the basis function psi 1 of t. For binary 1, we will be having the signal as S1 of t in BPSK modulation, that is having a magnitude of plus square root of EB with respect to psi 1 of t. So we can plot the point for binary 1 with a magnitude equal to square root of EB. So that is what we have plotted here. Whereas when we are transmitting binary 0, the signal is S2 of t, which is having a magnitude of minus square root of EB with respect to the basis function psi1 of t. So we can represent binary 0 with a magnitude equal to minus square root of EB. So this is known as the constellation diagram for a BPSK signal. Probability of error or bitrate of BPSK signal is given by P of E, which is equal to 1 by 2 ERFC, that is the error function of square root of EB divided by N0. So the above expression shows the probability of error depends only on the energy contents of the signal. As the energy increases, the value of the complementary error function, that is ERFC, decreases, and hence the probability of error will also decrease. Whereas the power spectra of a BPSK signal is given by power spectra of BPSK as equal to P into TB divided by 2 sin pi F minus FC into TB divided by pi F minus FC into TB the whole square plus sin pi F plus FC into TB divided by pi F plus FC into TB the whole square, and the bandwidth of BPSK signal is given by twice FB, where FB is equal to 1 divided by TB and TB is the bit duration. BPSK has various salient features, that is, it has a lower bandwidth, it has a very good noise immunity, it yields minimum probability of error, whereas the drawback of BPSK signal is it can have only coherent demodulation. In order to overcome this drawback, we go for differential phase shift keying. The next modulation technique what we are going to discuss is frequency shift keying. FSK is defined as a frequency modulation in which the frequency of the carrier signal is varied or shifted according to the binary symbols 1 and 0. The phase remains unaltered. FSK is an example of non-linear method of passband data transmission. The simplest form of FSK is binary FSK. So BFSK uses a pair of discrete frequencies to transmit binary information. That is, for binary 1, it uses a frequency F1 which is equal to the carrier frequency plus a small value. Whereas for binary 0, it uses a frequency F2 which will be equal to the carrier frequency minus the same value. And this technology is used for communication systems such as amateur radio, caller ID and emergency broadcast. We'll see how this FSK signal is getting generated. So the diagram shows the transmitter of FSK. So here the binary sequence is applied to on-off level encoder in order to generate D of t. So D of t is applied to product modulator 1 and product modulator 2. For product modulator 1, it's applied as M of t. The other input to the product modulator is the carrier signal square root of 2EB divided by TB cos 2 pi F1 t. And this D of t is applied to the inverter in order to generate M dash of t, which is then applied to product modulator 2. The other input to this product modulator is square root of 2EB divided by TB cos 2 pi F2 t. So the output of product modulator 1 and 2 are added in order to generate the FSK signal S of t. Say for example, when the binary sequence is 1, this on-off level encoder will be converting this 1 into plus 1 volt as D of t. And value of M of t which is generated for this is 1. And the product modulator 1 will be multiplying 1 with the carrier F1. So the output signal which is generated is S1 of t, which is equal to square root of 2EB divided by TB cos 2 pi F1 t. Whereas the same D of t is applied to the inverter in order to generate M dash of t. M dash of t will be 0. So 0 multiplied with the carrier, the output because of product modulator 2 for binary 1 will be 0. Whenever we are transmitting a binary 0, the on-off level encoder will be converting this into a 0 itself. So the value of m of t will be 0 and output because of product modulator 1 for binary data 0 will be a 0. Whereas this is applied to the inverter in order to generate m dash of t, where m dash of t will be equal to 1. So the product modulator 2 will be multiplying this one with the carrier square root of 2EB divided by TB cos 2 pi f2t in order to generate the signal S2 of t, which is equal to square root of 2EB divided by TB cos 2 pi f2t. So this is how the FSK signal is getting generated. So the received FSK signal can be detected by using coherent receiver. So the diagram shows the coherent receiver where the received BPSK signal is applied as one of the input to the correlator, that is a multiplier followed by the integrator. The other input to the correlators are the locally generated coherent signals. So that is square root of 2EB divided by TB cos 2 pi f1t and square root of 2EB divided by TB cos 2 pi f2t. Now the correlator outputs are subtracted and the resulting difference is indicated as y. The y is applied to the decision device. The decision device will be deciding such that if y is greater than 0, it will be deciding in favor of binary 1. If y is less than 0, it is going to decide in favor of 0. If y is equal to 0, it will be generating a random output. So the same BPSK signal can also be detected using non-coherent receiver. So the diagram shows a non-coherent receiver. So the received BPSK signal is applied for bandpass filter with frequency equal to f1 and bandpass filter with cutoff frequency equal to f2. The output of these two bandpass filters are applied to the envelope detectors, which are then compared by the comparator. So if the comparator is unipolar, then the output of the comparator is the bit sequence which was transmitted. So that is how the BPSK signal will be converted back into binary zeros and ones using non-coherent receiver. The diagram shows the waveform of FSK signal. This is the carrier signal what we are considering. Whenever we are transmitting binary 1, the frequency what we are going to transmit will be greater than the carrier frequency. Whereas for binary 0, the frequency which is transmitted will be less than the carrier frequency. Next we'll see how to plot the constellation diagram for BPSK signal. So whenever we are transmitting a binary 1, the FSK signal is indicated as S1 of t equal to square root of 2EB divided by TB cos 2 pi f1t. And for binary 0, it's indicated as S2 of t, which is equal to square root of 2EB divided by TB cos 2 pi f2t. Let us assume psi 1 of t as equal to square root of 2 by TB cos 2 pi f1t and psi 2 of t as equal to square root of 2 by TB cos 2 pi f2t. So substituting square root of 2 divided by TB cos 2 pi f1t as psi 1 of t, S1 of t will be equal to square root of EB psi 1 of t. Similarly, S2 of t will be equal to square root of EB psi 2 of t. So this psi 1 of t and psi 2 of t are known as the basis function, and we know the rule, the basis function will be perpendicular to each other. So now let us consider the imaginary line along x-axis as psi 1 of t and along y-axis as psi 2 of t. So now for binary 1, the FSK signal will be having a magnitude equal to square root of EB with respect to psi 1 of t. So we can represent binary 1 with the magnitude equal to square root of EB with respect to the axis psi 1 of t. Similarly, for binary 0, the FSK signal is having a magnitude equal to square root of EB with respect to psi 2 of t. So I can represent binary 0 with a magnitude equal to square root of EB corresponding to psi 2 of t. The probability of error for FSK signal is given by P of E, which is equal to 1 by 2 ERFC square root of 0.6 EB divided by N0. So from this expression it is clear that the probability of error depends only on energy contents of the signal. So as the energy increases, the error function decreases, further decreasing the probability of error. So the power spectrum of BPSK signal is given by this equation, and the FSK signal has a bandwidth equal to 4 FB. So BPSK signal has various advantages such as the simple circuit is needed, the generation is easier, and it has a constant modulated signal envelope. The drawbacks of BPSK signal are the bandwidth is greater than 4 FB, which is almost double than that of the bandwidth required for BPSK, and the error rate of BPSK is more compared to BPSK, and only half of the transmitted energy carries the information. The next modulation technique for our discussion is differential phase shift keying. DPSK is the non-coherent version of binary PSK. In DPSK, input sequence of binary bits is modified such that the next bits depends upon the previous bit, and therefore in the receiver, previous received bits are used to detect the present bit. Mathematically, we can represent the DPSK signal as follows. So binary data B of t is converted into a differential data by the relation D of t equal to P of t exclusively or with D of t minus 1. So now this differential data is applied to BPSK modulator with the carrier equal to S of t given by square root of 2EB divided by TB cos 2 pi FCT. Whenever D of t is equal to 1, the same carrier is transmitted and the signal will be represented as S1 of t, which is equal to square root of 2EB divided by TB cos 2 pi FCT. But whenever D of t is equal to 0, the carrier has a phase shift of 180 degrees and it is represented by the signal S2 of t, which is equal to square root of 2EB divided by TB cos 2 pi FCT plus pi, that in turn will be equal to minus square root of 2EB divided by TB cos 2 pi FCT. So next we'll see the generation of a DPSK signal. So the diagram shows the transmitter of a DPSK signal. The input binary data B of t is applied to the logic network in order to generate D of t, and this D of t is such that it is equal to B of t exclusively or with D of t minus 1. So D of t minus 1 is obtained by passing D of t through a delay element. So this D of t is applied to the amplitude level shifter, which is going to produce the output as plus or minus 1 based on the condition that when D of t is equal to 1, it is going to generate plus 1, and when D of t is equal to 0, it is going to generate minus 1. So this plus or minus 1 is applied to the product modulator. The other input to the product modulator is the carrier signal square root of 2EB divided by TB cos 2 pi FCT, and the output of the product modulator is the DPSK signal. So this signal is transmitted and received by the receiver. So this DPSK signal is given to the multiplier. The other input to the multiplier is the delayed version of DPSK signal to generate C of t. So C of t is applied to the integrator, and the output of the integrator is S1 of t, which is given to the decision device. So the decision device will be having a threshold value equal to 0, and it will be deciding in favor of binary 1 whenever S1 of t is greater than 0, otherwise it will be deciding in favor of binary 0. The advantages of DPSK system is it does not require carrier at the receiver and the bandwidth requirement of DPSK is reduced than BPSK. Whereas the disadvantages of DPSK are the probability of DPSK is higher than BPSK and the noise interference DPSK is more. In DPSK, previous bit is used to detect the next bit and hence if error is present in the previous bit, detection of the next bit can also be wrong and hence the error is created in the next bit too. Or we can say DPSK ends up in error propagation. Quadrature phase shift keying. In QPSK, the information carried by the transmitted signal is in the form of phase of the carrier. So, two successive bits in the data sequence are grouped together in QPSK and this reduces the bit rate and the bandwidth of the channel. So, QPSK is interesting one because it actually transmits 2 bits per symbol. In other words, a QPSK symbol doesn't represent 0 or 1. Instead, it represents 00, 01, 10 or 11. The combined 2 bits are modulated by selecting one of the 4 possible carrier phase shifts, that's 45 degrees, 135 degrees, 225 degrees and 315 degrees. QPSK allows the signal to carry twice as much information as ordinary PSK using the same bandwidth. Mathematically, QPSK signal can be represented as SQPSK of t, which is equal to square root of 2e divided by t cos 2 pi fct plus 2i minus 1 into pi by 4, where I is equal to 1, 2, 3 and 4 and E is equal to the symbol energy and T is equal to the symbol duration, which will be equal to 2 times TB. Applying the value of I, we get S1 of t for 10, S2 of t for 00, S3 of t for 01, S4 of t for 1 and 1 with the corresponding phase shifts pi by 4, 3 pi by 4, 5 pi by 4 and 7 pi by 4. So in this equation, apply the formula for cos A plus B. So we get SQPSK of t as equal to square root of 2e divided by t cos 2i minus 1 into pi by 4 cos 2 pi fct minus square root of 2e divided by t sin 2i minus 1 into pi by 4 sin 2 pi fct. QPSK constellation diagram can be obtained as shown. So we know the equation for QPSK signal. Let us assume psi1 of t as equal to square root of 2 by t cos 2 pi fct and psi2 of t as equal to square root of 2 by t sin 2 pi fct. Applying this in the above equation, we get Si of t as equal to square root of e psi1 of t cos 2i minus 1 into pi by 4 minus square root of e psi2 of t sin 2i minus 1 into pi by 4. Let us replace square root of e cos 2i minus 1 into pi by 4 as Si1 and square root of sin e sin 2i minus 1 into pi by 4 as Si2. So we get the equation for Si of t as psi1 of t Si1 minus psi2 of t Si2. So now psi1 of t and psi2 of t are called as the basis function and these basis function will be perpendicular to each other. So I am just considering an arbitrary line along x-axis as psi1 of t and along y-axis as psi2 of t. So now whenever I is equal to 1, the input debit will be 1, 0 and since I is equal to 1, the phase shift will be pi by 4. So now sin 2i minus 1 into pi by 4 will be equal to sin pi by 4 for I is equal to 1 and that in turn will be equal to minus 1 divided by square root of 2. Similarly, cos 2i minus 1 into pi by 4 will be equal to cos pi by 4 for I is equal to 1, and that in turn will be 1 divided by square root of 2. So applying this, we get Si of t as equal to square root of e by 2 psi 1 of t plus square root of e by 2 psi 2 of t. So I can say my Si1 will be plus square root of eb by 2. Similarly, Si2 will be square root of e by 2. So now, with respect to psi 1 of t, the magnitude what I have is square root of plus e divided by 2, and with respect to psi 2 of t, we have the magnitude as square root of e by 2. So we can mark the point, and that is the representation of 1, 0. Similarly, when I is equal to 2, the debit will be 0, 0, phase shift will be t pi by 4, Si1 will be minus square root of e by 2 with respect to psi 1, and Si2 will be plus square root of e by 2 with respect to psi 2. So marking the points, we will be getting the value for 0, 0. Similarly, I equal to 3, we get the point here, and when I is equal to 4, the input debit will be 1, 1, phase shift will be 7 pi by 4, and the magnitude will be plus square root of e by 2 and minus square root of e by 2. So we get the point here. So this gives the constellation diagram. So the probability of error or bit error rate for QPSK signal is given by ERFC square root of EB divided by 2 N0, and the power spectra of QPSK signal is given by PS into TS sin pi FS TS divided by pi FS TS the whole square. The bandwidth of QPSK signal will be equal to FB. The generation of QPSK signal. So the diagram shows the transmitter of QPSK signal. Here the binary data 1 and 0 is applied to polar NR set, and the polar NR set will be assigning plus square root of E whenever the binary data is 1 and minus square root of E when the binary data is 0. So this is applied to the demultiplexer in order to generate S odd of t and S even of t. S odd of t is given to the product modulator, and the other input to this is square root of 2 by t cos 2 pi FCT, and S even of t is applied to the next product modulator with the input square root of 2 by t sin 2 pi FCT. The output of both the product modulator is added in order to generate the QPSK signal. So the generated QPSK signal is received by the coherent detector, so which will be having the correlator. So first correlator is applied with the carrier square root of 2 by t cos 2 pi FCT, and this will be generating the output signal S1 of t. And the second correlator will be provided with the carrier square root of 2 by t sin 2 pi FCT, and the output of this correlator is S2 of t. So once S1 of t is applied to the decision device, it will be deciding in favor of 1 when S1 of t is greater than 0, otherwise it's going to decide in favor of binary 0. Similarly, once S2 of t is applied to the decision device, it will be deciding in favor of binary 1 when S2 of t is greater than 0, otherwise it will be deciding in favor of binary 0. And this is applied to the multiplexer to get back the original binary data what we transmitted. So it has various advantages, that is the bandwidth required by QPSK is reduced to half, and the carrier power remains constant as amplitude remains constant, and the transmission rate is high. Whereas the drawbacks of QPSK signal are noise immunity is poor and ISI is large in QPSK. Quadrature amplitude shift keying. If the amplitude and phase of the signal is varied, it increases the noise immunity. A system involving amplitude and phase shift keying techniques is called as quadrature amplitude shift keying or quadrature amplitude modulation. It has two quadrature carriers, cos 2 pi FCT and sin 2 pi FCT. Mathematically, QAM signal can be represented as follows. A QAM signal is represented as S of t, which is equal to K1 into A psi 1 of t plus K2 into A psi 2 of t, where psi 1 of t is equal to square root of 2 by Tb cos 2 pi FCT and psi 2 of t is equal to square root of 2 by Tb sin 2 pi FCT, and the value of A will be equal to square root of 0.1 into Es. Applying these in the above equation, we have S of t as equal to K1 square root of 0.2 Es divided by Ts cos 2 pi FCT plus K2 square root of 0.2 Es divided by Ts sin 2 pi FCT. So Ps will be equal to Es by Ts, hence S of t will be equal to K1 square root of 0.2 Ps cos 2 pi FCT plus K2 square root of 0.2 Ps sin 2 pi FCT. This is the mathematical representation of QAM signal. So next we'll see how the QAM signals are generated. So input binary data is applied to serial to parallel converter, wherein the output of serial to parallel converter will be 4 bits BK, BK plus 1, BK plus 2 and BK plus 3. BK and BK plus 1 are applied to a digital to analog converter in order to generate AE of t, and that is given to the product modulator. The other input to the product modulator is square root of Ps cos 2 pi FCT. So the output of the product modulator is X of t, which is equal to AE of t square root of Ps cos 2 pi FCT, where AE of t will be equal to plus or minus square root of 0.2 or plus or minus 3 times square root of 0.2, whereas BK plus 2 and BK plus 3 is given to another D to A converter to generate A0 of t, which is multiplied with square root of Ps sin 2 pi FCT in order to generate Y of t, such that Y of t will be equal to A0 of t square root of Ps sin 2 pi FCT. X of t and Y of t will be added and it gives the QAM signal S of t, which is equal to X of t plus Y of t. So this QAM signal is transmitted and received by the receiver. So the received QAM signal is applied to the blue color part, wherein the carrier signal will be extracted, that is square root of Ps cos 2 pi FCT and square root of Ps sin 2 pi FCT. Since it is a coherent detection, we need the same carrier what we used in the transmitter. So S of t is simultaneously applied to two correlators in order to generate AE of t and A0 of t. AE of t is applied to ADC, that is analog to digital converter, to get BK and BK plus 1. Similarly, A0 of t is applied to analog to digital converter to get BK plus 2 and BK plus 3. So these 4 bits are applied to a parallel to serial converter to generate the original binary data, that is B of t. So this is how the QAM signals are generated, transmitted and recovered back. So the QAM signals has various advantages, such as it has a reduction of transmission bandwidth and two separate data symbols can be simultaneously sent by the same carrier using QAM. The carriers do not interfere with each other in the transmission path in QAM. Whereas the disadvantages of QAM are noise immunity is poor than QPSK, the error probability is higher than QPSK, and it is relatively complex. So the table shows the comparison of all the 5 modulation techniques what we discussed so far.